Good morning. My name is Greg Wadley, and I'm with CTC and Associates. I'm the Clear Roads Administrator. We're here for the final project webinar for the project entitled GRIP Sensor Technology in Salt Applications. This research effort was led by Laura Fay of the Western Transportation Institute at Montana State University. Webinar is being recorded and will be posted on the Clear Roads website, I guess would be early next week for your viewing and those of your colleagues as well. We also ask that if you're speaking, or that unless you're speaking, excuse me, please remain off camera and keep your microphones on mute. However, if you do have any questions or comments, please enter them into the chat box and we'll address them at the end of the presentation. I think that's it for housekeeping issues, so I'll turn it over to you, Laura.
Great, thank you, Greg. I'm gonna share my screen, the presentation mode. If there are any questions or comments, I cannot see the chat pod, but please is that the correct
I'll let you know,
format?
Laura.
Okay, thank you. Is that the correct viewing format, Greg?
Yes, it is.
Okay, thank you so much. All right, well, thank you everyone for making it. This is the final report presentation for the Clear Roads Project 21-01, titled GRIP Sensor Technology and Salt Applications. This project was started a while ago, given the 21-year designation, and we were able to get a few extensions with the goal of capturing more winter data. So we're going to talk about this project now. So a quick overview of the effort required. This project included a literature review, a survey, development of case studies, which were used to identify data sources, the development of an algorithm or decision matrix for the application of GRIP in salt application rates, development of recommendations, and then here we are with the final report presentation. So I'm going to run through the project objectives just as a quick reminder. The goal of this project was to examine GRIP or friction as a viable data source for informing winter maintenance operations. And the goal was to identify what it is, where it comes from, how it's being used, the methods specifically for applying GRIP data, and different tools that are using GRIP data in winter maintenance operations. This project did a large job in the early phases with the literature review and survey of synthesizing information on how GRIP is used in winter maintenance operations, then used all of that for the development of a novel model, essentially, that applies GRIP data to help you decide reasonable application rates given the friction values present on the road. So I mentioned that we did a literature review. We worked to identify different sensor types. So whether these are stationary mounted sensors, typically as a part of an RWIS network. There are also mobile sensors that can be mounted on trucks and snowplows, other vehicles. And then kind of the newer category, which is floating car data or crowdsourced data. And we identified a few of the vendors that are out there or companies that are using this data that you can pay for to either get the data or have them apply the data for you. Conveniently, while this project was going on, FHWA's Everyday Counts 6 program had a crowdsourcing for advancing operations. And I just listed below some of the state DOTs that were highlighted as a part of this project and program. And you can actually follow that link in the presentation to see the different case studies they developed on how they're using crowdsourced data. So I mentioned stationary or mounted RWIS. We identified actual products and provided links to the companies if you're interested. We have updated this to make sure all the links are live and current. And also note that one vendor, the vendor at the bottom, no longer provides this sensor. So we noted that. We also identified mobile friction or grip sensors that are available in the US market. And again, the one at the bottom is no longer manufactured and available in the US. So when using GRIP data, we found that agencies are using it for real-time decision-making. So maybe they log into their RWIS network and they see that friction values are dropping and they need to deploy folks to get out there. They might use it for planning, whether friction is slowly decreasing as a storm's coming in and they need to call folks in, or for post-storm and post-season reviews, which is a great use of data after the fact. Some examples of applying friction or GRIP data include what Idaho is doing. They've created what they call a mobility index that essentially determines the amount of time that GRIP was below 0.6 in a percentage of hours. And they essentially rank or rate their winter maintenance operations on achieving this mobility index. Another example is what Utah DOT is doing. They're essentially equating friction values with different storm scenarios and different precipitation types. And ideally, you want to be in the green. You want to have good friction. And unfortunately, if you get into the red, then you're going to have to get out there and get your equipment working on the road. They note that yellow is acceptable. So acceptable can be in the range of 0.3 to 0.5. We'll get into some friction values in a minute, but these are tied to specific weather conditions and likely also deployment of vehicles. Looking across to Europe, they also use friction a lot, and I would say maybe even a little longer than in the US. And they use a little more, I guess, lower values. I'll just say that. You can see here for the example from Finland, they've defined different road conditions and associated GRIP values. And if you look at the satisfactory winter condition, that's from 0.2 to 0.24. That's significantly lower than most folks in the US would be comfortable with. We also report data from Sweden and Norway, which fall within similar ranges, and they break it out by road type, so road classification, and then even from high volume to low volume roads, they might have completely different metrics in which they determine if a road has reasonable friction or not. As I mentioned, in Europe overall, they seem more comfortable with lower friction values, whereas in the US, most states use around 0.5 to 0.6 as the threshold of when operations are needed to head out to recover them. So many performance metrics can utilize GRIP data, but what we've found is that the application is really unique to each transportation agency. Just the difference between the Idaho application and the Utah application are pretty significant. So the great thing is that you can do your own thing, or you can work off of what someone has already created and build out what you want to do with the GRIP data. Some example metrics using GRIP data are determining when to treat the road. So does friction or GRIP drop below 0.4 or 0.24, whatever your threshold value is? And then determining the time required to bring a road back. So maybe it's one of your level of service guidelines. GRIP data and friction data are also used in decision support tools, and we found quite a few papers out there that have done this. They use machine learning to predict surface condition and salt application rates. There were a few examples of this out there. Some of them used road condition categorically, so good, fair, difficult, or hazardous. Some used it to assess roadway surface, so icy is dangerous, snowy or slushy to bare or wet. And then again, what we were trying to get at, which is using machine learning to determine the amount of salt or in this paper's case, abrasive, that would need to be applied to bring grip back to a safe value. Other machine learning applications that we found included predicting efficient decision making, determining variable importance. So by variable, we mean road state, air temperature, pavement temperature, precipitation type, amount. So which variables need to be included in the different models. And then there are even some examples of AI decision tools that are out there. These are very early days in terms of the AI tool that's out there, but it is possible to use AI in this form. So I mentioned that we conducted a survey and we asked folks, how is their grip data collected? And the bulk of agencies are using stationary RWIS-based sensors to collect grip data, but then also a large number are either also or instead of using mobile sensors. Very few agencies are using skid trailers, which kind of shows a shift towards maybe using more modern technology. It's a little easier to collect the data, but maybe the quality of the data is not as wonderful as a skid trailer or friction trailer. So we wanted to know how agencies were using the data, and the bulk of agencies indicated that they're using it for real-time decision-making, followed by material application strategies and planning. There were quite a few other options noted that are in the report, but essentially the bulk of folks are using it for the same. And then we asked folks if they're using this great grip data in any tools that may be a part of their normal winter operations, and over half said yes. So the number one example was post-storm reporting, evaluation of winter maintenance operations, or evaluations of tools like the Weather Severity Index tool that they might be using. Other folks are incorporating GRIP into MDSS using an application that was developed within that, or using real-time decision-making tools. And other folks are even incorporating GRIP into public travel notifications. So I believe there was a project through Aurora going on at the same time that was using GRIP data to inform variable speed limits. And that project just wrapped and is available on their website as well. So really interesting applications of GRIP data. And then a last piece of this that I'll present on are the case studies that were developed. So we used the information from the literature and the survey to develop 4 different case studies. I'll just highlight them here, but there's significantly more detail provided in the report. One project that was going on at the same time as this one was working to link spreader controller data with mobile RWIS data. And they were using the Vysula MD30, which is a mobile sensor, and they were specifically using grip data and other variables to determine what the spreader should put out on the road. This project was done in conjunction with Massachusetts DOT and University of Massachusetts at Amherst. And the goal was to develop a decision-making algorithm for the material application so that the spreader controller did the heavy lifting, making the decision. Ultimately, they were able to deploy the mobile sensors on 2 different plows, and they were able to connect the mobile data with the spreader controller, which is a lot of work because they're not a part of the same system. So a lot of effort went into hardware integration, software development, road surface condition, deep learning, so development of an algorithm to link the two, and then coming up with that salt prediction model for the spreader controller. And ultimately, they were able to find some success with 34 to 37% salt savings when modeled. So this project will continue, I hope. The final report can be accessed at the bottom. And I believe Mark, I saw him on the call. I think he was either an active part of the project or is very aware of the project. So that was great that that was going on in conjunction because there was a lot of overlap and they were very helpful for us in this effort. Another case study was based on the advancement of the work in Idaho. So they've had their mobility index for a while now, and they use it well. But they were trying to make a more integrated system working with a company, Esri. And the goal was to develop an application suite to automate, visualize, and communicate the mobility cost efficiency calculations that they use. So they worked with them to develop a live view, a statewide seasonal view, and then a historical view. So kind of a retroactive view of what's going on. And it gives them access to mobility across the entire state. So here's a few images of what this might look like for them. These are just screenshots that were shared with us. But essentially it's building up their mobility tool, which is great. The third application or case study is the use of friction data in an MDSS program called Pike Alert. This was a project in conjunction with Alaska DOT and NCAR, the provider of Pike Alert. So basically it's a normal MDSS tool, but they tailor them to the actual agency and the agency needs. And in this case, they really wanted GRIP data incorporated. Key data elements that are utilized include precipitation, road surface condition, visibility data, and also blowover risk was a factor there. So the Pike Alert system is providing treatment recommendations and alerts based on the unique characteristics that Alaska identified. And specifically at the time of this case study, they were starting to use the GRIP data and find out how they can apply it within Alaska's specific MDSS. So they are going to use friction data to monitor road condition and help with decision making and then future forecasting efforts. So that's an ongoing project still. And the final case study is third-party friction data. So that crowdsourced data or floating car data from vehicles. And interestingly, Iowa DOT is partnered with Iowa State University to purchase what was WEJO data, but is now Streetlight. And we also worked with Nera Dynamics, who is a foreign European company that uses European vehicle floating car data in their methods for this case study. And essentially what they have access to is data from up to 13.7 million connected vehicles. Now within Iowa or within a specific place in Iowa, they may not have access to that many vehicles, but they're figuring out how they can use this data. Essentially, the data provides vehicle journey information. So time, location, speed, and event. There's nothing that ties this data specifically to a person or a vehicle itself. So there is anonymity in there, which is great. And essentially, this is what at the time they were working through. They were working to figure out how to use the data, to build confidence that the data can be applied by Iowa DOT in different ways. And initially they were going to start trying to figure out safety applications, but there is interest from the winter maintenance group to apply this data as well. So here's an example of what one car's data might look like. So a journey starts and then maybe they activate the seatbelt warning, and that's in the data. And then they detect that the seatbelt is latched. And then the high beams come on, and then the speed increases, and then wipers are activated all the way until the journey stops. So someone might be going from their job to grab lunch or from home to pick up the kids. But you don't know that. You just know a car moved, and this is the data that was picked up from it, and that is overlaid on a map. So there are challenges with this as well. For example, you don't know if a vehicle slowed down necessarily because there was a crash or the person was looking at their phone and not paying attention, or or an animal crossed the road. So they're working to kind of tease out um, large vehicle decision making things, like if there was a slowdown, or all the vehicles around there slowing down, or was it an isolated vehicle slowdown. So there's a lot of work that needs to be done on this, but there are some companies like Neurodynamics and others that are already applying this data and do have winter maintenance specific tools. So at this point in time, I'm going to hand it over to Hal, and he's going to talk about the algorithm and modeling that he did, and how I can either share my screen for you or you can share yours.
Uh, Let me share yours if this is share mine if it's better.
Yep, I will stop sharing.
Okay, sure. Let me just open it now. Just 1 minute. Oh, sorry, the wrong one. Yeah, this should be the correct one. Are you seeing the PPT now?
Yes.
Okay, so let me go to page. Case study. Yeah, okay, task 4. Okay, now you should be able to see the full screen, right?
Correct. And you should go advance to
Oh,
slide
I still
25.
do. Yeah, sure. Okay, yeah, here it is. Yeah, okay. And thank you for the opportunity. Actually, we worked with Nora on this project. We are mainly responsible for developing algorithm and also decision-making framework that really can use the data coming from ARWIS and also AVL coordinates or vehicle tracking information, which providing also the salt application rates, so we can know how the friction is changing after salt application. And then by doing this way, we can make a decision what kind of more salt is needed or less salt should be applied, depending also on the climate condition. So in order to develop the algorithm, we actually collected 2 data sources. The first one is from our DOT, which provided ARWIS data and also the SORIS data from the plow trucks. Unfortunately, I don't think we have the plow condition data, which is something we can do in the further study. The second data set is from Colorado DOT. In this case, in addition to the ARWIS data, we have the mobile sensor data on surface condition. But this data period is relatively short, so actually that's why we use a different way to analyze this data set. And also we have the salt rate from the plow trucks. So the first data set is from Iowa DOT, which actually we have 1 ARWIS site. Initially, we identified 4 ARWIS sites, but look at the data concerning the data quality and also the slow storm events during the location. So 1 ARWIS site was finally selected. It has longer coverage of the data and also it has good data quality. So basically, we have 2 winter seasons, basically across actually 3 years. So first we did the data processing and integration. That means we have to integrate ARWIS data, which is stationary data, with the salt rates data, which actually changes with the truck. So we have to find out at the ARWIS location how many salt is applied, actually at what time, and also what's the snowstorm period for this location. And then with the data, we developed a machine learning algorithm. We'll talk about details shortly. And then we use the model or algorithm, conduct a sensitivity analysis. And then we also propose the framework to use the algorithm for event-based decision making. That means the salt application rate can be adjusted based on the individual snowstorm event, not just the kind of one constant value based on really the table or other ways. So the data processing and integration basically is integrating the data coming from 2 sources. First is ARWIS data, which has atmospheric variables, a lot of temperature, wind speed, and surface condition data. And also we also have the surface temperature data too. And in this case, we have to find out, okay, when this slow plow truck stops by the always location, apply the salt, and then what will be the friction measurements actually before and after. So by doing that, we'll be able to have the continuous time-dependent friction changing over the period, and also we know when the salt is applied during this period. So spatially, actually, we are using a 0.4-mile radius actually around the highway site because the GPS of the aerial truck is not always kind of showing it's exactly on the hours location. And also most hours side actually is also on those side instead of on the travel lane. That's why we kind of did a little bit of approximation here. So with the data integration, you will see a few examples here. This actually shows you during the snowstorm events, basically what will be the snowstorm period, because not all the periods our data actually having snowstorm. And then you can see where the slow start and end, and also you have the friction measurements actually coming from the sensor at every 15 minutes. Unfortunately, for the Iowa DOT data, we don't have the numerical value for the grip value. It's only showing low, medium, and high. So you can think about low is more like considering as not a safe condition, slippery condition. Medium is like around 0.4, 0.5, and high is a little bit more like a dry condition or no slow or basically wet condition. That's why I can see during a slow storm, there's very few dry cases. But you will have the dry cases or high grip action in the period between different snowstorms. So for example, the first one give you, in this case, we have a salt application actually before the slow and also in the middle and even a little bit after. The second one actually has more frequent slow salt application. I can see these rates also, most of them concentrated in around 100, but we do see a variation for this case, actually as small as less than 50, as high as more than 200. We didn't do further processing for these salt rates. We use the data as it is coming from the aerial data sensor. So by looking at all the slow storms, actually 26 events over these two winter seasons, we're first looking at what's the general idea, what's the period of snowstorm. So you can see the left figure tells you in two different seasons, typically this snowstorm spans across like a few days, as long as like 4 or 5 days. That's very few, but most of them like 1 to 2 days or 3 days. And then during the snowstorm, for the salt application, depending, this is the first time, first salt application during the snowstorm or second or third. I mean, most of them have at least two times the salt application. Some of them have 3. So you can see the salt application rates actually also plotted in the bar chart here, box plot here. So basically, this one gives you the median value, mean value, and also 25th and the 75th percentile in the box. So that's the majority of the data we have. So usually they are around 100. But we do see the variation from 50 to 150. So basically, that's the current salt rates has been applied based on the field data. So with this data, we are able to develop something called a non-short-term memory model, which is one type of something we call the recurrent neural network model. The difference between this recurrent neural network model versus traditional neural network model is it does have a time dependent factor. So that means not only the input features affecting the output in the previous step also affecting the output in the next step. So in that case, it's more like I have the time dependent issue. So in this case, we're talking about we have those atmospheric variables. We also have the friction before the salt application, and then we have the salt application. So all those factors affecting the friction after the salt application. So for example, if you're using traditional neural network model, probably only thinking the input features that only have the atmospheric variable and the salt, and then you are predicting the grip. But here we do consider the history of the grip development, which actually is important because when you apply the salt, the existing condition also makes a impact on the post-treatment condition. So that's why we can consider sequential effect of the input features, not only just the discrete effects. So with this way, we'll be able to use this as a decision-making tool. For example, if I do have the history of the salt application and also have the grip before the salt, I'll be able to predict step by step what will be the friction or grip in the next 15 minutes after this salt is applied or no salt is applied. So we're talking about this prediction is over this time window. So with any machine learning algorithm, you want to test the model accuracy. So basically, we have 80-20 data splitting. Here shows you actually the testing data accuracy. So you can see most of data we are actually capturing that, especially for the high, because we have so many high grip. If that's no slow actually happened, that's actually why the high grip level accuracy is very, very close to 1. But actually, we are more concerned about the medium than low. So here the accuracy is considered as acceptable, although it's not very high. The medium accuracy is about 0.67 and no accuracy is about 0.692. F1 score can be used as a combined score from the precision record to indicating accuracy. Although the accuracy is not very high, but we do believe this is actually acceptable and actually indicates the potential. Again, we also only have 2 winter seasons data. If I have more data, we'll be able to train the model with a better way. So that's why I said, okay, we model is acceptable. So let's see if we can use the model to derive some useful findings. So first thing we did is with the developed model, we simulated all the 26 slow storm period. And then we used the start application rate using the field as a baseline. And then we artificially, saying, I'm changing these start application rates by -50, +50, and also +100. So seeing, what's the changing of the friction instead after this change. So the left figure gives you a summary of this changing. So we're counting, how many observations are medium, how many are low. The blue one is for the medium, the red one is for the low. So you can see as we're increasing the start application rates, we can see the reasonable trends actually have more medium grip level observed rather than also the less low grip level observed. So this trend actually is making sense. We also look at it if we have more salt versus less salt. Is the timing from the start application to the timing when the grip level is improved? Is this actually also has been changed or not? So actually we're also seeing if we have more salt applied, we do see actually the grip level increased actually quicker. This actually is around like a 10 to 20 minutes interval. So that means you are observing this medium level grip actually when since we have 15 minutes in the data interval, basically 1 or 2 basically intervals ahead of the traditional one. So that definitely actually shows the amount of the salt, its benefits. But again, the exact benefits were depending on the individual condition. So that's why we also said, let's just use the model to propose the event-based framework. That means we do have the weather condition, we have the data from ARWIS. So with the also with the grip measurements actually before the storm or at the beginning of the storm. And then with the model, we can predict what will be the grip level changing over the time as we continuously having the climate condition, weather changing, and also salt applied. And then we can see, at what time, you will see actually the grip value actually every 15 minutes as recorded. So, but you will be able to predict ahead of time. And then you'll be able to see, if this start application rate is able to produce the grip is accepted, for example, from jump from low to medium in this case, then it's considered as acceptable. If not, you can see, I'm increasing more start application rates, and then what will be the grip value? So this is actually the manual process for now. There is a way to really automating this process with reinforced learning, which more advanced technique. But because of the project, this scope is really focused on developing this framework, so we didn't go further. And also, if you really want to automating the process, you need a huge amount of data actually to make this loop closed. But at least the framework is presented here. So with this framework, we tested, if I do have this framework, decision-making framework, if I have a certain atmospheric condition and also other conditions, what will be the impact of the salt? So in this case, you can see this is one selected slow storm events. And then we still using the baseline, which is the actual salt applied in the field. And then we said, if I'm increasing this salt by 50 or by 100 or -50, what will be the changing of the grip over the time? So you can see in this case, actually, we don't see too much changing by minus or reducing 50 pounds per lane mile salt. But we do see the improvement of the grip if we're increasing the salt application by 50, 100. And you can see clearly, if you do have 100 pounds more, you can see the changing of the grip level actually from low to medium actually getting one more ahead of time, 15 minutes more earlier. Again, kind of data is based on the 15 minutes interval because that's the training data shows. So that means we can use the LSTM algorithm developed to looking at what will be the possible changing of the grip as we apply different salt. Another case study we did here is we're also looking at the temperature effect because we know as the temperature is getting colder, we intend to apply more salt. Here, actually, we try to see, okay, if I have the same salt application condition, but I'm using different slow storm events which have different temperature. So what will be the impact? So first one shows actually one of the slow storm events, you have surface temperature 24, 26. And second one shows you have a little bit higher temperature, 27 to 30. We try to find a huge difference one, but unfortunately, the difference was then not big. But still, you can see here, if you compare the first one and the second one, as you have a lower temperature, which is the top case, after you're changing the salt rates, you have more obvious changing, especially if you're looking at the minus 50, for example, reducing the salt. In the surface, in the top figure, you can see, okay, we do see the grip level varied because the cross actually indicates actually have different with other labels. But in the bottom one, we don't see too much changing actually there. So that means actually the temperature also plays a role. So in general, we do see if the temperature is lower, the sensitivity of the grip level changing to the salt application also is more sensitive. That also proves actually this model is pretty effective. So in general, this LSTM algorithm serves as an engine which can be used to make a decision making what will be the salt applied using the LSTM method. As I said, we have two sets of data. Second set of data is from Colorado DOT, which actually has different data collected for the grip, which is from Tacoma sensor. It's the mobile sensor. Originally, we tried to use the same data set or collect as many as data to develop the similar algorithm, but turns out actually this is actually more like experimental sensor actually used by Colorado DOT, and they don't have really good matching between the Tacoma sensor and the geotap sensor, which from AVL. And also because of the data acquisition issue, we only get about 1 month of data. So this data actually limited how many data points we have. And also because mobile sensor, you are measuring the grip actually along the whole route. So you get good spatial coverage. But for one single location, this slow plow truck may only come back once or twice. So that means we will not have the grip changing over time as we had from the always sensor. This is actually, I think, one of the good interesting finding, the good or bad mobile sensor. Mobile sensor is good to give you very wide spatial coverage, but if you really want to looking at what will be the grip changing over time at one specific location, actually always sensor provide actually more information. So with this limited data, we changed the strategy a little bit. So instead of looking at the grip level changing over the time, we focused on what will be the delta, what will be the increase of the grip and the friction after salt application. And also this mobile friction sensor data give us a numerical value, so we'll be able to calculating what's the delta changing after salt. So in this case, we don't consider sequential effect. We just basically considering, okay, what will be the delta? What will be the increased amount of the friction coefficient depending on the salt and other variables here. So again, we have a lot of data cleaning here, basically try to looking at each location, how many times is AVL truck coming back, and is this truck applied the salt or not? And then we're looking at what's the friction changing every time when this AVL sensor coming back, because the friction sensor, Tacoma sensor, is on the AVL truck too. And always data here is just provided general climate data. So we didn't use the friction data from always for this analysis. So basically in this case, as I mentioned, the model is to predicting what's the surface friction changing, or actually here the friction coefficient exactly after salt application. And then we putting a lot of inputs here because we want to know what's the time period from the starting of the slow storm to the moment the friction is measured, and also the moment the salt is applied, because these two are not exactly the same as recorded by the plow truck. And also we also have some difficulty, and we solved eventually is because it turns out actually the baseline time of the two sensors are different because they're coming from two different manufacturers over the world. So we kind of need to convert to match the time. So basically, we have the time from the start of snowstorm to the time when the friction is measured, and also the time from the start of snowstorm to the time actually the salt is applied. So these are all the input variables, and also the surface condition, and also the salt application rates actually at different timing. So with that, we are using more simpler machine learning models. So in this case, you don't need to consider the time-dependent issue. So you just consider, okay, I have a bunch of inputs. I want to predict outputs. The output is the delta. The inputs is the timing between slow storm and salt or friction measurements, and also the surface condition, and also the salt. So we are using actually three most common machine learning models, SVR. Here actually it's a regression instead of classification. So it's a support vector regression instead of a support vector machine. And then random forest and also gradient boosting regression. So all these models actually will provide generally good accuracy. Here we are looking at the accuracy for the testing. Usually the training data will give you high accuracy. And if this difference is very high, and that means the model is overfitting. So here we have a little bit overfitting issue, but it's not significant because the testing accuracy are picking up. So in general, we have about 60-74% R-square in the testing data set. And then if you look at the predicted friction, it's around 0.1. That actually means the error range we have for friction. So here I'll give you actually the comparing of the data. So it's not perfect. Again, it's depending on the data, but in general, we're capturing the trend. But keep in mind, we do have 0.1 friction prediction accuracy with the data we have. But the model was able to predicting, okay, if I do have different salt applied, what will be the expected changing, which is not time dependent, it's for the individual measurements. So with that, actually, we focus more on looking at what will be the most affecting or influencing variable for the prediction. So this is something we call a sharp plot, which tells you the importance comparison of the input features from high to low. You can see the surface state after application is the highest one. This is expected because if you have the surface condition more like a dry, wet, or slow, then your friction value is quite correlated with that. And then you can also see the surface state before application is also very high importance. That also actually proves we should consider this one in the time-dependent model as we did for the first data set. And also you can see the timing of the measurement after the application is also important. That means also how long after the salt is applied after the snowstorm. So in general, this model gives you a more simple prediction. What will be the changing of the friction if you are using different salt? But by having two data sets with two different methods, we are still actually recommending the first model because that model is able to using the always data, the friction measurements over time, and also to looking at what will be the grip changing over time with the salt applied. And then with that, be able to adjust the salt as needed. So that's actually what we did for the task 4. And you have all the details in the report. Let us know if you need any more details or questions. Thank you for that. Yeah. Now you want me to go back to your screen? Hi, Nora, can you hear me?
Sorry about that.
Laura, if you're, oh,
Yep.
there you are.
Can you,
Okay.
sorry about that. I had muted myself. I'll take over from now, Hal. Thank you so
Okay,
much.
I can end the screen share. Okay.
Okay. So after that effort, the next task was to make some recommendations on how to use grip data and in this application specifically. So as you saw, use of complex models has its pros and cons. They can do a really good job of predicting, but they do require knowledge of modeling techniques. And that can be challenging if you don't have someone in your agency to do that. Then you're kind of dependent on a third party to do that for you. Another challenge we faced, or a future recommendation, is that a lot of these efforts that we did were based on limited data. There were, thanks to you guys, time extensions to capture additional mobile data. Unfortunately, there were challenges with identifying which vehicles actually had the mobile sensors on them and linking the mobile sensor data to the trucks through the AVL system. So the mobile data is only from 1 month. So if additional data can be included, we felt strongly that that second model could be improved. The other challenge is that the Iowa data was, the grip data was categorical, as you saw, so low, medium, high. And there was not an option to get the actual friction value. So in the future, if Iowa wanted to, they could work with the vendor to get the actual friction data and test the model with that. And that might improve its accuracy as well. And then also the variability of the influence of salt at cold temperatures, where the model showed that using, or we need to test the model using colder storms. You're only going to be able to model what the data shows. So if we just had a whole bunch of warm storms or short storms, low precipitation storms, that's all it can model for. So additional data, again, would be huge in terms of moving these forward. I mentioned communication challenges, and I think whenever you're doing a project with a lot of data, it's always good to have a communication plan ahead of time. For me, that was a huge lesson learned with this project. So setting up contacts within different agencies of who will be the point contact for the data, if the third-party vendor is involved, who their point of contact is, and if needed, setting up a data sharing agreement early in the project. We ran into a few issues of who actually owns the data and who has the right to access it, and then what are the easiest ways to get it. There are a ton of firewalls now between different agencies. So how do you streamline actually capturing that data? And then once you have that data, creating a crosswalk file, which is basically a database that says third-party vendor calls this variable X, the DOT calls this same variable X1, but they mean the same thing. And then sometimes our one other issue we ran into was that the units were not converted or were perceived to be converted from metric to English units. So really just paying attention to the details of where the data is coming from and does it make sense when you take a first look at it. So setting up a crosswalk file will really help with that. Again, with data considerations, that crosswalk file is super helpful. Additionally, looking at SALT application rates that are applied versus what the actual state or local agency guidelines are. We specifically with the data from Colorado, we saw a lot of lower application rates than were anticipated because their level of service guidelines recommended a higher application rate. So really checking in with the agency of, are these values correct? And if so, maybe using that AVL data to inform modifications to your level of service guidelines. And then as always, when you're using large data, QA/QC is critical. Bad data coming in equals a bad model coming out. So a ton of time was spent making sure that the data was high quality, that fed into the model. As always, there's always room for more work. Some examples of future work that we identified are testing these models using larger data sets, as we've mentioned, using these to look at cost and environmental impacts as well. So kind of expanding the models to look at optimum application rates. One thing that would be really helpful moving forward, I think for everyone, researchers, mobile sensor companies and DOTs, is if a test section was set up that was instrumented specifically for mobile data collection And those mobile sensors were run up and down that road multiple times, either daily, weekly, monthly, at routine intervals. That would really help simplify modeling. Right now, you're at the whim of when the plow happens to drive down that road. But if continuous data was able to be collected from these, I think a lot of really great insights could come from that. For this project specifically, future work could include also plow up and down, liquids versus solids, data that was not available to us, but could be available in the future as more DOTs are getting this data from their AVL providers. And then development of just a guidance document to address data needs, data management, and then agency coordination. Essentially all the hard lessons you learn working with 3 separate groups to try and get data for projects like this. So in conclusion, friction data sources are used in winter maintenance operations, and the data is typically coming from those stationary sensors, but also mobile, and kind of newly, a few agencies are working with that floating car or crowdsourced data. The data collection method, calibration, and QA/QC will influence the quality of how you're using that data. So they're all critically important. GRIP data is being used in winter maintenance operations for real-time decision-making, material application strategies, planning, and training and review of operations. Just to name a few, that's not all of them, but those are the major ones. And we did develop some case studies to highlight how GRIP data is used in winter maintenance. With the work by Rutgers, they found that the RNN LSTM models can predict friction evolution during storm events and recommend salt application rates. And those key variables that were identified by the model are roadway surface temp, air temp, salt application rate, and grip. And that grip appears to improve quicker with increased salt application rates, which when you think about it logically, that makes sense. The more salt you put out, the quicker you're going to get a return to good, safe driving conditions. This effort required complex modeling and data management, which is both a pro and a con. In the future, building out this model and strengthening it would be wonderful, especially to add in data for those kind of outlier or other storm events like colder events, longer events, high precipitation events, or even icing events. And the grip from stationary RWIS versus mobile RWIS also present their own challenges, where the RWIS data that we got was categorical versus the mobile data that was just limited by just 1 month of data due to other challenges. So with that, that's our presentation on this effort, and I will stop sharing so we can have an open discussion.
All right, thank you, Laura, I appreciate it. There are no messages in the chat right now. I know that there was one earlier from Mike Madison, and you addressed that in the chat as well. So if anybody has a question or comment, just go ahead and either you put it in the chat box or raise your hand. Go ahead, Mark.
Hi, Dr. Fay and Howe. Thank you very much for your work on this paper. Thanks to the subcommittee. I definitely think the future of roadway maintenance for us relies on delivering treatments that are prescribed based on roadway conditions and incoming weather. A colleague of mine with whom you're familiar, some of you are, Mark Valenti, once said, we're not in the salting business, we're in the grip maintenance business. And he was with the town of Lexington, but now he's with Brine Technologies. So Mark can help you, establish and maintain grip if you give him a call. They got great brine makers. This paper acknowledges that we've got an appetite for road weather parameter driven treatments and related protocols as an industry. And in the not too distant future, like Dr. Fay discussed, there'll be a more plentiful reservoir of data from mobile RWISs, connected vehicle fleets, and privately owned cars. And that will really, really help research efforts like CR 2101. which I believe we should review for retreading in a couple of years because so much data is becoming available. And thanks again.
All right, thank you, Mark. Does anybody else have a question or comment? Go ahead, Mike.
Yeah, I agree with Mark on the state of this technology and the importance of it. Here in Nebraska, we're doing some testing with some fixed location grip sensors and some mobile ones, and we're actually interested in using that information for the federal highways formulation for variable speed limits. And so the research that was provided here was really useful as we're looking at how we're going to approach the evaluation of these different sensors. Thank you.
Thank you, Mike. Does anybody else have a question or comment? Okay, hearing nothing, I want to thank the research team again for their work on this project and the project subcommittee for helping to guide that effort, including both Mike and Mark you saw there. This webinar will be, once it's completed or processing, I'm going to post it on the project page, also on the webinars and other videos page under the resources tab, and then the PowerPoint, once it's been tweaked a little bit, we'll go ahead and post that on the members page so that you guys can use it, with your own agencies, however you see fit. Laura, Hal, anything else you want to say before we sign off?
No, just thanks everyone, especially for your help with the survey, the case studies, and then also liaising with data access. And I agree. I think there's a ton of potential in the future, especially with incorporating AI and the floating car data. So it'll be interesting to see how this evolves over time.
Yeah, I agree with Nora. Thank you for the opportunity working with everyone. Thank you.
All right, thank you so much. Have a great rest of your day and a good weekend.
Thank
Bye,
you.
everyone.
Bye.
Thank you.